So today we're going to be looking at standard deviation and coding, both of which are fairly short topics. Standard deviation I think is going to be quite quick for you. Coding might take a bit longer, but overall it's not that bad. And again, as always, the worksheet and the mark scheme are both going to be uploaded right after this video. So if you would like to have a go at the work beforehand, you can do that. Or what I'd recommend doing is having the worksheet out in front of you, and then as I do one example, attempt the next example yourself, then continue the video. I'd also recommend a couple of days after watching the video, maybe 1 or 2 days, retrying the questions yourself and seeing how well you do. That way you can actually identify if you know enough. I would also like to point out that I did get a question before about, does this cover everything? This covers all the types of question you can be given. However, you do need to do some practice by yourself. The more practice you do, the better. And these questions are great for that, but of course you may want to look at other questions eventually. But anyways, without further ado, let's just get into it. So, when we look at standard deviation and coding, what is it? Well, let's start off with the coding aspect, because that's what's going to come up first in our questions. So, coding may sound like something that we do in computer science, and it is what we do in computer science, but coding is just a method by which we simplify data. So let's say, for example, I'm looking into house prices. Okay, so we'll say house prices. If we look at the value of house prices, you're probably going to get something in the hundreds of thousands region. So you might have something like 300,000, then you might have 350,000, you might have 400,000, and you might have 500,000, right? Those are some stereotypical house prices. Now imagine if you're actually calculating the median of those values. Well, that means you have to add up all of these numbers, and these numbers are quite big, right? 300,000 plus 350,000 plus 400,000 plus 500,000. What coding does is it allows us to simplify numbers. So for example, I might divide all of these numbers by 100,000. And now these new numbers are going to just be 3, 3.5, 4, and 5. Now, why do we do this? Well, there's two reasons. One reason is that bigger numbers are actually more taxing computationally. I'm not just talking about with your brain, but when you use calculators or computers, when you have very large numbers, it actually makes the program run slower and can cause it to crash. Now, of course, with 4 numbers, that's not going to be a case. But for example, some of the statistics we have in the UK are things like median house prices. That's the price of every house in the country, of which there are roughly tens of millions. That's where simplifying the numbers will make the numbers go a lot faster. You'll be able to calculate the average a lot quicker. And then, as we'll see later, you can actually uncode the median itself, and then you'll get what the actual value is. So for example, if you worked out the median of this number, I probably should have put another value, you'd get something roughly about 4. Probably 3.75 actually. Now, what that translates to in real life would be 375,000, which we can do very quickly. So instead of using all these massive numbers, we can then work out the value using simple numbers, and then work out what the actual value is. And again, that saves time computationally, which is really, really important. The second reason is probably a bit more nuanced. With statistics, what do we tend to do with them? We tend to show them to other people, and those people might not necessarily be mathematicians. So showing really large numbers, for example, if you're talking about stars, the masses of stars or the masses of planets, it's very difficult to have these masses, which by the way are normally look something like this, 10.25 times 10 to the power of 24. That number means nothing to the common person. It doesn't mean anything. In fact, it barely means anything to scientists. So if we code the data, we can make the numbers more manageable. So for example, if I'm comparing the masses of 2 planets, and I have something like this, if I divide them both by times 10 to the power of 24, instead I have something like 7.25 and 6.24, which is a lot easier to actually visualize the number, to see how much bigger it is. Okay? So those are a few situations where you might do coding. And how do you do it? Well, it's essentially the same as what I've just done. You can divide, you can add, you can subtract, and you can times. You can't really square or do anything like that. Normally we just add, subtract, times, or divide. Okay? And that's really important. And as you can see, we'll have some kind of formula like this. And I'm going to show you what that exactly means. So if you're coding data, you just sub the values in and work out what the value is. Nice and simple. But you're going to be uncoding as well. So I hope that makes sense. Now, what about standard deviation? What is the standard deviation? And I'm going to show you the different formulas and everything shortly. What is the standard deviation? The standard deviation tells you how far on average values are from the center. So that might sound really strange, but let me visualize this for you. Let's say we have our values along the bottom, and we have the number at that specific value. So for example, it could be the height of people in centimeters. You expect it to have a bell-shaped curve around the median, which we normally give as a mu. The standard deviation will tell you effectively how wide this peak is, how spread out your data is. So it's a new measure of spread, which is very, very accurate. It's more accurate than the range and the interquartile range. Okay? So just as a visualization, if you have something that has a very low standard deviation, it's very sharp. So low standard deviation, low SD. You have a very sharp peak because that width is very small. Whereas something with a very large standard deviation will look something like this. Can you see that that data is far more spread out? So again, it's a measure of spread, and the higher the standard deviation, the greater the spread. It's basically saying that on average, these values are further apart if they have a high standard deviation. Low standard deviation means that they're very close together. And a standard deviation of 0 means that all the values are the mean. Okay? So, how exactly do we work it out? Well, the standard deviation is a very interesting formula that you get given. But here is the actual formula for it. So standard deviation is given by the letter sigma, and it equals the square root of the sum of fx squared over n squared minus the sum of fx over n squared. I know it looks really strange, right? But let's break this down for a second. This thing here is literally the same as the mean. And this fx and fx squared you should recognize from the mean. Okay? So it's the frequency times the midpoint of the classes. So that's actually okay. N is the number of pieces of data that you have. So overall that's not too bad. And I would like to point out that they normally give you these values here, the sum of fx squared and the sum of fx. And I may even show you later on how to do this all on a calculator anyway, by entering in the data yourself. But it's very situational because calculators don't just do it for every single table that exists. Hopefully that gives you a bit of a brief introduction into what standard deviation and coding are, but let's actually get into doing some of these questions. Okay, so let's get on with the first question. Now you may notice that this is the exact same question as we did in the linear interpolation video. However, we only did part A, and we're going to do part A from scratch as if we haven't done it before, just to give us a little bit of revision. And again, as we go forward, this is going to come up a few more times where we've only done part A, maybe A and B of a question. So in a later video, when we learn about the other topics in stats or mechanics, we then go through A, B again, plus also C, D and E. So this is something you should expect, and it's actually a good thing. It means we're going to automatically revise previous topics, and I've said this many times, but A-level maths is very interconnected, so please be aware of that. So again, we have this coded times frequency. We need to use linear interpolation to estimate the mean of the median times. So all we have to do for that is we start with part A, we do n over 2, so the number of people in this is 50, How did I know that? Well, there's two ways. You can either add all of these up, or you can just look at the sample size over there. And we'll get our calculator ready as well, just so we have that available. And what it was just on was for another video. And we need to actually use linear interpolation. So if we do this, we're looking for the 25th value. And all we do is we go up, and so that would be the first value, then there's the first 10 values, then there's the first 29 values. So I know it's in this class over here. And if you remember what you have to do, again, if you're unsure about what I'm about to do, please go back to the previous video in linear interpolation just to get some practice with that. So the first thing you do is you take the difference in the actual class that you're looking at. So in this case, we're going to do 15 minus 10. And that is going to be over the median minus 10, because remember, the median is somewhere in between 10 and 15. We just need to work out what it is. Then we take the difference in the cumulative frequency, so 29 and 10. And the bottom part is the 25th value, so 25 minus 10. And then you just need to do some rearranging in order to work this out. Again, use just a calculator, nice and easy. So 29 minus 10 over 25 minus 10 gives me 19 over 15 on the right hand side. So 19 over 15, probably could have done that in my head, but oh well. 15 minus 10 is 5 over Q2 minus 10. You can do this a lot faster with the rearranging if you'd like, which completely up to you if you want to. I'm going to times both sides by Q2 minus 10 to give it a 19 over 15 Q2 minus 10. Then we're going to times by 15 and divide by 19. So that would be 15 times 5 over 19 equals Q2 minus 10, which means Q2 is just, if we do it up here, Q2 is equal to 15 times 5 over 19. That is a 19 over here, by the way. Doesn't look like it. Plus 10. So let's work out what that would be. So we have 15 times 5 over 19 plus on another 10, which gives us an answer of 13.947 blah blah blah. Let's keep it as 13.9 as our estimation for the median. And if you notice, that is in between 10 and 15, so that does make quite a bit of sense. And now we get on to the actual new stuff, which is standard deviation and the coding. So first of all, let's start with the standard deviation. So that is part B. Now, if you look back at the standard deviation formula, we have this. So if we just copy this or move this over, let's keep it next to us. We can look at the kind of stuff that we need. So the first thing we need is we need f times x and also f times x squared. And remember, this sigma symbol, so it's a capital sigma, means sum of. So all you're going to do is add 2 new columns, maybe 3 if you'd like. And the first one is going to just be fx. Remember, frequency is f, and x is either the value in this column or it's the midpoint, depending on what kind of data you have. So here we have grouped data, so we need to find the midpoint. However, sometimes it's just a single value, in which case you don't need to use the midpoint. So that's why I said maybe 3 columns. So I personally just like to write it next to it, so the midpoint of each of these, so 2.5, 7.5. Remember the method I told you on how to work out the midpoint of any 2 numbers. You just add the numbers together, so 0 plus 5, and then you divide it by 2. That automatically gives you the midpoint in case you get numbers that are a bit weird. And here will be 12.5, here would be 20, and here would be, so this is maybe a slightly trickier one. So you just do 25 plus 40, gives you 65, divided by 2, 32.5. Okay? So either way you want to do it. And these values here are our x's. So f of x is literally just going to be 1, in this case, times 2.5. So it's going to be 2.5. Here's going to be 9 times 7.5. In fact, to make this slightly easier, we're going to actually get rid of the numbers from the previous part because we don't need the cumulative frequency anymore. So let's just get rid of that, or we can leave it for a bit later. So the next one would be 9 times 7.5. 9 times 7.5. 67.5. Then you have 19 times 12.5. those of you that are perhaps have already spotted a slightly faster way to do this, or if you're wondering if there's a faster way to do this, I want you to know that there is, and I'm going to show you that a bit later on. So this is kind of the longer method of doing it, but at the same time it will ensure that you have a correct method, because what you don't want to do is try and use a shortcut that you don't fully understand and then end up getting the wrong answer, because then it defeats the purpose. At the end of the day, you want the right answer rather than a quick answer. Okay? And what I mean by that is, if you remember how calculators work, you can actually do all of your calculations in one go. So at the end, what I like to do is I like to add them all and put them in their own little box at the bottom. So all I'm going to do now is add up all of these numbers. So we have 2.5 plus 67.5 plus 237.5 plus 280 plus 227.5. It should also be noted that a lot of the time they actually give you these values. However, I wanted to include an example where they don't give you them, just so you can see where these numbers come from, in which case, just in case your mock or your real thing just happens to not give you the values. I don't want you being caught out with your pants down, so to speak. Now, fx squared might look a bit tricky, but all it is f times x squared. So quite literally, it's just going to be 1 times 2.5 squared. And that's it, 6.25. And you do this for all of the other values, just like you did in the first one. So here the frequency is 9. And again, we can just change these numbers, make it 7.5. Gives you 506.25. I will show you a slightly faster way of doing this, but at least once do it the kind of longer, tedious way, just so then you can actually properly appreciate the slightly faster way of doing things. And this one is 12.5. Gives us 29. Okay, that's quite a big number. 2968.75. 2968.75. And then we have 14 multiplied by 20 squared. That's going to be a pretty huge number. So you should expect the fx squared to be quite large. That's completely fine. Nothing wrong with that at all. And last we have 7 times 32.5 squared. So we have 7 and we have 32.5 all squared gives me 7393.75. So 7393.75. Add them all up. So once again, start from the top. So 6.25 plus 506.25 plus 2968.75 plus 5600 plus 7393.75. Another good technique, by the way, is to count how many numbers you have here. So we have 5, and then count how many you have in your calculator. Missing one is very, very common. So 1, 2, 3, 4, 5. Add those all up and we get a pretty hefty number, 22,493, blah, blah, blah. So I'm actually going to put it underneath the box because my box is not big enough. 493.75. And now it's just a matter of subbing it into this formula. Okay? So, I'm actually going to just do it all on the calculator. So press square root, fraction button. You have sum of fx squared, which is going to be this bottom number here. Because remember, we've added them all up. So 22,493.75 over n squared. So it's over 50 squared. Then you are subtracting, open bracket, the sum of f of x over n. Once again, you should hopefully realize that this is just the mean. So if you've worked out the mean in the previous question, you can just sub that in squared. But just for this case, 815 over 50, and that answer is all squared. And that gives us a, 1 second, something went wrong. Let me just check it out. Okay, so I spotted the slight mistake. I actually put an n squared here, and it's meant to just be n. So the actual formula is just n. So that was my mistake. I think I was just trying to think ahead. But either way, the actual formula is the sum of f of x squared over n minus the sum of f of x over n all squared. And that does give you the correct value of 13.6. Okay, So that was a 2-mark question. Not too bad. However, we have a 3-mark question here, which basically says, calculate the mean and the median and the standard deviation of the original data. And that is actually quite interesting, because here, just remember, all of these are coded. So they have they've had this done to them. They've subtracted 20 from every value and then halved it. So now we got onto how the mean, the median, and the standard deviation are affected by this coding. Because to uncode this, let's look at this. So we have x is equal to t minus 20 over 2. And what you might say is, okay, let's rearrange for t, and that would be a smart move. So times both sides by 2 gives me 2x equal to t minus 20, and therefore t is equal to 2x plus 20. And then you might say, okay, all I need to do is sub in both of these values into this formula and we get the original data. So remember, this is the median of x and the standard deviation of x, but we want the median and standard deviation of t, the uncoded data. And that is half right. So for the median, and here are some notes for you, it's affected by times, divide, add, and subtract. And hopefully this makes sense. So let's say if I had a bunch of data, and it was like 1, 3, 5, and then actually let's make the numbers even more simpler so we don't have any confusion whatsoever. So if 1, 2, 3, 4, 5. Okay. Now you might say the median is 3. But if I double all of these numbers, right? So we have 2, 4, 6, 8, 10. The median also doubles, right? So if I times them all by 2. The same would happen if I divide it, right? The median would go back to 3. So it's affected by times and divide. Makes sense, right? But what if instead I, let's say, added 10 to every value, yeah? Then once again, the median changes. And how does the median actually change? Well, the median follows the same pattern. If I double all of the values, the median doubles. And if I add 10 to all the values, the median gets added by 10. And if I divide or subtract, the same thing happens. Because times and subtract are just times and divide are just opposites, add and subtract are just opposites. So they affect each other the same way. So in this case, with my median, since I've subtracted 20 and divided by 2, the actual median is going to be 20 more and double. So the median for this data is indeed 2 times 13.9 plus 20. Just using this exact formula to go from the coded median to the uncoded median. And let's just quickly do this on the calculator. So 13.9 plus 20. And that gives us 47.8. That makes sense to us, I hope. So the actual median is 47.8 minutes. Okay. What about the standard deviation? Well, I told you that the standard deviation is a measure of spread. So what's another way of measuring spread? It's the range, right? Well, if I have a look at these values here, how does the range change? Well, in this first example, the spread of the data, if you use the range, is 5 minus 1, which is 4. And what about in this data? Well, it's 15 minus 11, which is still 4. The data is still as spread out as it normally is. So adding and subtracting does not affect the standard deviation. The standard deviation just tells you how spread out the data is. It doesn't matter if you shift the data left or right, it will not be affected. So SD, standard deviation, is only affected by times, divide, only. But again, if we look at this example, if we times them by 2, what happens to the range? Well, 10 minus 2 is 8. Well, the range is twice as big. Again, with this particular example, range and standard deviation is effectively the same. They tell you about spread. With standard deviation, it just tells you how far on average the values are from the median. okay? But we can use the range not for actual specific numbers, but as a kind of an analogy, okay? So because the range is unaffected by adding and subtracting, it means all the measures of spread are unaffected by adding and subtracting, whether that's interquartile range or standard deviation. So when we do the standard deviation, when we work out the real standard deviation, we ignore the plus 20. Instead, the standard deviation is just going to be twice as big, okay? Which is going to be 27.2 mins. I hope that makes sense, but keep in mind, you don't technically need to understand this, you just need to remember it. But as I've said in all the videos up till now, whether they're the pure statistics, mechanics, whatever, it is so much easier for A-level maths if you understand something rather than just memorizing it, because memory is not perfect. You will make a mistake at some point. So go through that one more time. If it still doesn't make sense, feel free to leave a comment, feel free to email, leave a message, whatever. And if it comes to it, I'll schedule a video call with you and I'll go through it again. But effectively, adding and subtracting doesn't change how spread out the numbers are. It only affects, the only thing that affects how spread out the numbers are is timesing and dividing. So keep that in mind. And that brings us to the end of the first ever standard deviation and coding question. So what I'd like you to do is have an attempt at the next question and then watch the video again to see what the answer is. But I'll see you in the next question. Okay, second part. Hopefully you guys actually had an attempt. Now, if you notice, the first thing I'm spotting, and I'm hoping you spotted it too, is these numbers do not overlap, which means we need to change what the actual class widths are. So that way there is actual overlap. So please never forget this. Like I said, I have A2 students, year 13s, that are doing some complicated maths that forget this very basic rule, which is another reason why you need to keep revisiting previous topics. It may be easy, but I guarantee you there's one small little thing you forget about, and you know, it screws you over. Now, thank God, have a look at this. They've given us sum of f of x and sum of fx squared, which means we do not need to do it. Thank God. So they are kind of nice in that case. However, use linear interpolation to estimate the median height. Again, this is from a previous, from the question that we did last time, but I hope you had a go at doing this. Don't skip it. Use every opportunity you can to revise previous topics. And if you get the answer wrong, there you go. There's an early warning system for you. Go back over it. So linear interpolation, how do we do it? First thing we do is take the number of values and we half it. What's the number of values? 100 people. Or add up the frequencies if you're nice and paranoid like I am. So that's 50 values, the 50th value. So if we add this as we're going up, we have 4, 23, and then I can see straight away that it's going to be in this class over here. So what do? We take the difference in the class boundaries, so 29.5, or we just take the class width, if you want to say it in a bit more of a human way, over the 50th value, or in this case we're looking at Q2, minus the lower class width. And that equals the difference in the cumulative frequencies, or just equal to 41, whichever one's your preference, over the actual value we want, which is the 50th value, minus 23. And once again, just do some movie magic with your values. So if we just first work out what these are, so the one on the left is actually quite easy, I don't need to do that. Q2 minus 19.5. Work out what the thing is on the right, just to make our lives slightly easier. 64 minus 23 over 50 minus 23. 41 over 27. Nice and easy. Again, you can call it cross-multiplying if you like, whatever you prefer, or you can do it in kind of two different steps. So first times up the denominator of the left-hand side, which gives you Q2 minus 19.5. And then we're going to times by 27, which gives us 270, and divide by 41, equals Q2 minus 19.5, which means the final answer is going to be Q2 equals 270 over 41 plus 19.5. Nice and lightning fast. 2 marks, again, it shouldn't take you that long. So they do have quite high standards in terms of how quickly you write all this stuff out. 26.1 I'm going to call it. So when in doubt, it's nice to just do 3 significant figures. And then parts B and C, this is so quick. This is 3 easy marks, okay? Estimate the mean height. Remember what the mean is. Normally what you do is you do frequency times the midpoint, add them all up. But that is the same as this. So this is another reason why notation is very important. Some students would waste time working out what the midpoint times this is, adding it all up and then realizing it's just 2651. Well done. You've wasted a minute, maybe 2. All it is the sum of f of x. So the mean is the sum of f of x over... The sum of f is the technical way of writing it, but sometimes that confuses people. So 2651 over the 100 people here. So I'm not even going to use a calculator. 26.5 to 3 sig fig. Which means lastly but not least, standard deviation. It is a formula you are given. But, remembering it doesn't hurt either. Sum of fx squared over n minus the sum of f of x over n all squared. And like I said, they've given us these values, so this is nice and easy. You could also use this mean in here, squared, but I do prefer entering the whole thing again, even though it doesn't seem like the smart thing to do. So 804, 34.25 over this n, which was 100, minus 2651 over 100 squared. 10.1, let's call it. So that was 6 marks in total, and if you have a look at how long it's taken us, it's not 6 minutes. And you could probably do it even faster once you start getting really good at it. The mean and standard deviation should not take you 4 minutes, to be honest. At the moment, it's okay if it's taking you more than 4 minutes. Just putting that out there. But by the time of the exam, this is going to be quick fire, nice, easy marks that you won't make mistakes on. Hopefully. And then we come on to doing the mean and the standard deviation for ungrouped data. So this is, again, the main reason why I wanted to put this in here is just to illustrate how the formulas change. So we know that the mean is the sum of f of x over n, and then we have the standard deviation formula as well. But what happens when we don't have a midpoint x? Well, if you actually think about what this is here, the midpoint, it's the actual value of the data, right? The frequency isn't the value of the data. The actual value of the data here is the midpoint. So the thing that disappears isn't x, the midpoint, it's f that disappears, okay? Because we don't have a frequency. It's not that we don't have the data, we don't have the frequency. So with the mean here, all we're going to do is we're going to add up all of the pieces of data and divide it by the number of data we have. And I like to do this all in kind of one step on a calculator. So top is just going to be adding all of these up. So 45.2, 46.9, 46.1, 46.2, 45.4, 45.1, 47.8, lost my space, 45.4, 45.5, 46.1, 46.4, and 45.7. So let's just go through and make sure we get it. Do it backwards. So one key thing is not to read through the numbers in the same order again. So one thing they actually use, you tell snipers to do this, is to go in the opposite way to what you normally read. So we normally read left to right, top down. If you want to actually spot mistakes, you read right to left and down up. So we can't really do down up here, but we read it right to left. So 45.7, 46.4, 46.1, 45.5, 45.4, 47.8, 45.1, 45.4, 46.2, 46.1, 46.9, and 45.2. And what it does, it forces your brain to actually pay more attention. And we have 12 athletes, so it's just divide by 12. There we go. So 45.9, so we should probably round this to 3 significant figures. So 46.0 to 3 sig fig. Now what about for the standard deviation? Once again, it's just going to be the exact same formula, but we just delete the f's. So how is that going to look? Let me show you. So it's the sum of x squared over n minus the sum of x over n squared. Okay. So here we're probably going to have to do this separately. But what we can do, if we're quite clever, is we can actually use this. So what we're going to do is we want to delete the fraction, and that's just the sum of x. So now we have the sum of x is equal to 551.8. And how do we get the sum of x squared? Well, all I need to do is go through and put a squared sign after each digit. So there, squared, there, squared, there, squared. Actually, I don't know why I'm using... And if you actually remember the spacing between each number, because they're all the same number of digits, you can actually do this a lot faster. So you just go, I think, what would it be? It'd be 1, 2, 3, 4, so 5 to the right. So 1, 2, 3, 4, 5. Boom. 1, 2, 3, 4, 5. 1, 2, 3, 4. Oh, no, I got to the end. 25, 380.38. So 25, 380.38. And then we just need to sub it in. Nice and easy, hopefully, possibly. So we have the sum of x squared, so 25, 380.38 over the 12 athletes minus 551.8 over 12, and that is squared again. 0.75, 7.51. Like that, 0.751 to 3SF. So if that's not too bad, hopefully so far it's been okay. But again, I would like you to have a go at the next question before you kind of look at the video if you can. Okay, and for the final questions, the final kind of type of question is about the large data set that they may give you. And the data can look a bit confusing because it's real world data, which tends to be a bit messy. But it's the exact same stuff that we've been doing for the past few videos, including this one. And as you may notice, there is no part A, and there's a few other parts missing because, once again, large dataset question has normally 4 or 5 parts, but they're outside the scope of this video. First thing we need to do, in this particular case, is use linear interpolation to calculate an estimate for the upper quartile. So, yeah, linear interpolation is not just for median, it's for the upper and lower quartiles as well. You just need to remember the different formulas for all of them. So upper quartile is 3n over 4, and the lower quartile is just n over 4. So let's do it. We need to work out what the frequency is. However, what we can do is add all them up, right? It's not the hardest thing in the world. 12 plus 17, so it's 184. So now if we put this into our calculation, 3 times 184 over 4. And what I'm going to do, because I know that I'm going to forget, is I'm going to write that the sum is 184, because that is going to be useful a bit later on. We're looking for the 138th value. It's actually not as hard as it seems, because this is already at 121. It's 131. That's going to be 155, yeah. So it's definitely in this range here. So that's nice and easy. So once again, we're going to do the difference in the class widths, 5 minus 1, over Q3 minus 1 is equal to difference in the cumulative frequencies, 155 minus 131, over 138 minus 131. Again, nice and easy, nice and standard. So we have 4 over Q3 minus 1 equals, and then whatever the heck that is on the other side. So we have 155 minus 131 over 138 minus 131. 24 over 7, okay, it's a bit simplified, that's nice. Actually, no, it isn't. What am I talking about? Do the good old-fashioned timesing to the other side. We get 4 is equal to 24 over 7. Q3 minus 1. I would like to point out that since your algebra is going to get a lot better over these next 2 years, or until you finish A2 anyway, you will be able to do this a lot faster than I'm showing you right now, because I'm taking it nice and slow, just on the assumption that you might still be slightly weak, which is okay. It's okay to be weak, it's just not okay to stay that way. So 7 times 4 over 21, add another 1 for good luck, and that will be Actually, let's put the equals on the underside just to keep it nice and neat. We have 7 multiplied by 4 divided by 21, add another 1. 7 over 3, so that's 2.332 significant figures. And with the standard deviation, we already know it. Nice and easy. All we need to do is we're going to use sigma equals, let's write out for the last time in this video, sum of f of x squared over n minus the sum of f of x over n all squared. Like that. And they give us the values. Look how lovely and kind the examiners are. So 7704, 0.1875 over n, which I said was 184, perfect, minus 539.75 over 184 squared, 5.77. And the number being small should hopefully make some amount of sense because it is rainfall. Okay, so it does make sense for it to be a relatively small spread. And that's it for standard deviation and coding. It doesn't really get much harder than that. With the coding, I would recommend finding other problems to try and practice. So going back to here with the coding times. But it really is just this. If you know this, if you're comfortable with this, you can do coding. It really does not ever get harder than that. It's nice and easy. It affects the median in all ways, times, divide, add and subtract. And it only affects standard deviation by timesing and dividing. It's pretty simple. So again, if you find another example, it should be nice and easy. But again, the mark scheme is going to be online. The worksheet is going to be online.